10-4, that's a go, buddy. We're going to call this one Lecture 1 on source frequency resonant circuits. Yeah, and this is, of course, honored after Mr. Tesla over there. A friend of mine did this remarkable, Doc did this remarkable portrait of him. I got mine behind there too. I'm going to use it for a gravestone. But what we're going to look at here is we got 1.5 ohm inductors from a 465 hertz alternator. Let's see if that thing can be shown. And right now what we're testing is where I left off on the previous video, which was unacceptable due to some mistakes on placing shorts. Right now we got a short across all three of them Li quantities. If I can find the dang stick. Yeah. Yes, we have shorts across Li here on phase 1. Each phase has voltage meters and amperage meters at the center between the LC values. Now we call this L interphasal because we've arranged for a tight mutual induction between all three phases magnetically. Ci is also the interphasal measurement needed to cancel the reactance of Li's reactance measurements. So right now we've got Li and Li and Li shorted out, and presumably the short will negate the influence of any current going on the inductor. That's a further measurement that can be made. However, here we need to start out and quickly get this thing done. We're actually measuring the, it's a resonant test of the 666 machines. Then we have to devolve into that again. Having problems with my eyes at 60 years old, folks, I tell you. There we are. 666 machine is so named because each of these phases are wrapped around each other in a barber's pole color scheme, and the middle phase, if in fact it were not wired identically to the other phases, each of them columns should be producing canceling magnetic fields via the fact that it's a three-phase input attached in delta series resonances. However, that does not occur. There's other reasons for that, and I played with making primary systems designed only on three columns like that, but eventually it came to a balance arrangement where I could arrange this thing somewhat like a magic square so that we could attain equal currents on the phases. And then we get an increase of inductance relative to that it would be experienced if its phase were engaged in isolation. So we can try to test that then. And over here again I wanted to mention each of the segments of this device consists of two coils of 100 feet, 200 feet per segment, arranged in a bifilar manner. At one time we did experiments with triangular arrangements, and that's why some of the coils are arranged in triangle form and one in circle. We've removed all the secondaries and we're investigating the reactance of the system. We'll turn the machine on now. It makes a lot of noises from a three-phase alternator, and we'll see what we get without a field. Then we'll engage the field for more precise observations. These things take a while. We've got to get here and done. Evidently the field's already turned on. God, goody God. Let's see what number 3 is doing. Does a nice balance. Those capacitive reactance to the 3-phase input at 13.6 microfarad are balanced all within a tenth of a microfarad. So it's kind of unusual to see such a balanced occurrence. And now, by looking at the simultaneous, what the 666 machine does, you're recording a wave by the meter. Because one of the segments flies off in time and starts rotating faster than the rest of it. And it happens every 24 cycles. And what you read from your meters is that 24 cycle wave of that extra segment going up and down and influence the relative observations on the outputs. Okay, now we've seen the reactance. To compare, I said that there's a 1.5 R load. We go back to the schematic here again. There's a 1.45 ohm load on there. And now all we need to do is take all the shorts off the L quantities and we'll be able to see the resonant rise of voltage enabling a proportional higher amount of current that we're seeing now on the meters. Correspondingly, both the 6-volt inputs and those amperages will change when we remove the shorts and let everything go resonant. For this problem, I found that when things are balanced, sometimes you have to enable the balance to be continued. We've got a good looking balance, and we're going to turn the machine off, take the shorts off, and then turn the machine back on. Then we'll see the full amount of resonance occurring in this 1.5 ohm 666. Quickly taking the shorts off of the system. I should have looked before, but I can see short on phase 1 removed. Where's phase 2 at? It's going to come from phase 2 stator wire. There's a short. Right there it is. Phase 2 short removed, and we should be able to remove phase 3 short here momentarily. See if I can, is that the green one? Yeah, that looks like phase 3 short. Now we'll turn the machine back on. Okay, folks, there's what happens with the 1.5 ohm resonant load down hits what was formerly shown on the reactive output to the 6 volts. So there's the maximum energy transfer in play. Now we have to end here and show the opposite reactance so that we have the resonant test, and that's simply done by shorting each cap system. We run in there and do that while it's live. Number 3, about 0.96 now phase number 1. The averages that have happened on these phases when we do these things aren't always going to get detected. Not at all. Now then, we can record what the reactance on the values are. We can take pictures of each of these conditions now, and we've shown what should be capacitive reactance on the three-phase output and what is now an inductive reactance on the three-phase outputs. And in this case, it looks to be fairly balanced. And we're 11 and a half minutes now. Now we need to show what one of the phases in isolation would do. And we're going to choose phase number 1, which is conducting 0.204 amps to 5 amps. We're going to set the other phases down. And when we do that, we can see what the inductance would be in isolation. So we're looking at phase 3, down to 0. We're looking at phase 2. Sometimes these things happen. Like I said. We're on phase 2. Okay, we've got that. Now we can look at the new reactance conditions for that phase number 1, which are 5.2, 5.3 volts, enabling 0.274 amps. And now we can compare the reactances from the solitary condition to the one in the interphasal condition. And what I've already found is there's a 30% difference, and so we'll call this done.